This video is going to be about experiment 6B in a digital analog conversion, and it's an introduction here about the fact we live in an analog world where we have to digitize things to put them into computers, that is the values of things. So already in Circuit Maker I've taken the data for this particular circuit. So here you see what happened. Turned out that the input data word in binary was through the switches 0, 1, 1, 1, 0, 0, 1, 0, and the output was 1.140 volts. Okay, so then took and put different data words and hex in. The first one was 07 hex, which is shown up above here as this value in binary. 5 zeros followed by 3 ones. Then we put in 0B in hex, which is shown down here. 0F in hex, 10 in hex, AA in hex, C2 in hex, F8 in hex, and FF is all ones, 8 ones. So I took in, those are the values I got, the measurements. The next thing we did was change the reference voltage, doubled it, and put in these values for the data words. That is what the switch conditions were. So the conclusions give you a equation here. V out equals the input in a base 10 number times the voltage reference divided by 256. So in this chart here I say convert the value input data words into output voltages. So let's just take a look here. Get my pen. For 07, the input data word was 5 zeros. I'll put it up here. 5 zeros followed by 3 ones. In base 10, that would actually be 7. Okay, up here I got 4 plus 2 plus 1 in binary, which adds up to 7. V out measured was 70 millivolts. The equation up here says that V out is equal to, well, we had 7 for the input, base 10, times is 2.56 divided by 256. 2.56 was the reference for that table. 256, we X this out, and it's 7 times 0.01, which is 0.070, which is equal to 70 millivolts. So we're happy, but that's how you should go through the rest of that table and make those calculations. So that one came out just about exactly. Now let's do one more. AA in binary, AA was 10101010. Okay, so you got to convert that to decimal, and I would tell you that that's equal to 128 plus 32 plus 8 plus 4, 2. So 8 and 32 is 40. 2 and 128 is 130, so that's 170. So that's what the digital input is, 170. The output measured was 1.7 volts, and you might get the drift here that if we do the calculation here of 170 times 2.56 all over 256, we'll end up with, that'll cancel out, give me 0.01. So 0.01 times 170 is equal to 1.7 volts. And that's exactly what we got out here. 1.7 is the calculated measured value. So that's how you would do that table. If you go over to this table, it's the same thing. The only thing is that the reference voltage has changed. So let's do one of these. I'll go back up here. Let's take 1F. 1F is 0, 0, 0, 1, followed by 1, 2, 3, 4 ones. And the voltage we measured for 1F was 620 millivolts. So 620 millivolts. What's this in decimal? Well, in decimal, this guy has a worth of 16 plus, that guy's 8, plus 4, plus 2, plus 1. 4 and 16 are equal to 20. 8 and 2 is equal to 10, says 31. So the word in decimal is 31. The equation was that V out is equal to input base 1031 times now is 5.12, all divided by 2.56, which is equal, if these things cancel, it's equal to 31 times 0.02, which just so happens to be 620 millivolts, which is exactly what we have here. So these things work perfectly, and again, there's only one problem, that is, as you do it, what happens, there can be what we call quantizing error. So it's a you want to use the most number of bits you can. Of course, 8 bits work very well for what? For computers that have memory locations of 8 bits or 1 byte. But we can take and actually, convert a number by using 2 memory locations and using 16 bits and feeding it into a 16-bit D-Day to convert it. Okay, so that's this little video about the results for experiment 6B.